me ask you a question. Can we build a lakehouse architecture and an entity resolution solution in 15 minutes? Technically, yes. Can we also explain it properly in that time? Only if I speak at double speed, skip every pause, and temporarily stop breathing. The hands-on build is quick. The rest of the video explains what is happening behind the scenes, so we do not simply press run, see a few green ticks, and immediately update LinkedIn to Enterprise Lakehouse Architect. We will take messy data through bronze, silver, and gold, then work out which records belong to the same real-world entity, without accidentally merging half the organization into one person. This is a compact proof of concept using 3 small datasets. In production, with hundreds of tables, millions of records, security reviews, testing, and approvals, it would take a little longer. For today, we are keeping it small, practical, and fast. Let us start the clock. We have been hearing a lot about the Medallion architecture. It is often presented as the modern architecture for building large, complex enterprise data platforms. You have probably seen diagrams showing data moving neatly from bronze to silver to gold. It looks great on a slide. But what is actually happening behind the scenes? What does each layer really do? What data should we keep? What should we clean? And where should business rules actually live? Well, in this video, we are going to build both capabilities. Of course, this is a proof of concept. The goal is not to build a full enterprise master data management platform in one video. The goal is to show that these concepts are not as abstract or mysterious as they sometimes appear. We are going to look behind the architecture diagram and implement the actual logic using Azure Databricks, PySpark, Unity Catalog, and Azure Data Lake Storage. We will start with 3 small sample datasets. The first dataset contains customer information from a CRM system. The second contains financial transactions, and the third contains contact records from a fictional case management system. The datasets are intentionally imperfect. They contain duplicate records, mixed date formats, invalid dates, malformed email addresses, missing transaction amounts, transactions linked to customers that do not exist, names with spelling differences, and names written in different orders. In other words, they contain the kinds of issues that make data engineering interesting. We will first use the customer and transaction datasets to build a medallion pipeline. We will preserve the original data in bronze, clean, type, deduplicate, and validate it in silver, and then create consumption-ready customer and transaction tables in gold. After that, we will bring in the third dataset and build a rules-based entity resolution capability. We will standardize names, generate possible matching pairs, calculate fuzzy name similarity, apply explainable matching rules, create an entity cross-reference, and produce a golden record for each resolved person. Then we will take the solution one step further. Databricks is not only a Spark processing platform, it also includes AI and business intelligence capabilities. We will build an AI BI dashboard from our gold data. We will create an interactive entity search dashboard, and we will configure Databricks Genie so users can ask questions in normal language. For example, find people named Smith, or which state had the highest customer spending. Genie can translate those questions into SQL and query the governed data behind the scenes. So, by the end of this video, we will have built a repeatable Azure environment, a governed Databricks Lakehouse, a complete bronze, silver, and gold pipeline, an explainable entity resolution process, golden customer entities, an interactive search dashboard, and a natural language analytics experience using Databricks Genie. That is quite a lot to cover. So let us begin with the 2 main ideas behind the solution. The Medallion architecture organizes data into 3 progressive layers: bronze, silver, and gold. Each layer has a different purpose and a different level of trust. A useful way to remember the architecture is bronze preserves evidence, silver establishes trust, gold answers questions. Let us break that down. Bronze, preserve what arrived. Bronze is the raw ingestion layer. Its job is to preserve what the source system provided. It should not try to be clever. It should not remove duplicates. It should not fix names. It should not guess data types. And it should not silently remove invalid values. For example, one of our customer records contains an impossible date, the 31st of February. That is clearly not a valid date. but bronze should still preserve the original value. Why? Because that value is evidence of what the source system actually sent. If we immediately convert it to null or discard the record, we lose that evidence. Keeping the raw data also allows us to rebuild downstream tables later. Maybe our date parsing logic changes. Maybe a business rule was wrong. Maybe a source system begins sending a new format. If bronze still contains the original data, we can replay the pipeline without asking the source to send the information again. Silver, create trusted source data. Silver is where the data becomes clean, typed, and reusable. This is where we trim unnecessary spaces, standardize uppercase and lowercase values, parse dates and timestamps, convert financial amounts into proper decimal values, remove duplicate business records, validate email addresses, and check relationships between datasets. However, the silver layer in this POC follows an important principle: flag problems, rather than immediately deleting records. For example, our transaction data contains a transaction linked to customer C999, but customer C999 does not exist. Instead of deleting the transaction, Silver keeps it and creates a flag called has Gornos known customer. The value becomes false. This gives us visibility. We can count the bad records. We can investigate them. We can build a data quality report. And if the missing customer arrives later, the transaction is still available. If we had dropped it earlier, that information would be gone. Gold, prepare data for consumption. Gold is where the data becomes ready for a specific business purpose. This layer may contain dimensions, fact tables, aggregations, business metrics, features for machine learning, search capabilities, or datasets designed specifically for dashboards and AI tools. Gold is allowed to make stronger decisions. For example, a reporting table should not include a transaction with a missing amount or an unknown customer. Those records remain visible in Silver, but Gold can exclude them from trusted reporting. This means the rule is implemented once in the pipeline. We do not need every dashboard developer to remember the same filters. We do not want one dashboard excluding negative amounts while another includes them. Gold gives us one governed definition. And that makes the dashboard much simpler. At this point, you might ask, why do we need 3 layers? Why not load the file, clean it, and create the report in one step? For a tiny one-off analysis, that may be fine. But as soon as the platform grows, several problems appear. First, the original data may be lost during cleansing. Second, every downstream consumer may implement its own version of the same cleaning rules. Third, business logic starts accumulating inside dashboards. And fourth, when something goes wrong, it becomes very difficult to determine where the issue was introduced. The layers give us separation of responsibility. Bronze tells us what arrived. Silver tells us what the trusted source record looks like. Gold tells us what is ready to consume. Now let us look at the second major concept. Entity resolution is the process of deciding whether records from different systems refer to the same real-world entity. That entity could be a person, an organization, a property, a device, or almost any real-world object. In this POC, we are resolving people. Our CRM may contain C001, John Smith. Our case management system may contain CT01, John Smith. These records have different IDs. The names are not identical. But they may still represent the same person. Entity resolution attempts to make that determination using the available evidence. Most entity resolution systems follow a similar process. 1. Standardization. 2. Candidate generation. 3. Similarity scoring. 4. Match classification. 5. Clustering and survivorship. Stage 1. Standardization. Different systems represent data in different ways. One may store John Smith. Another may store Smith John. Another may include punctuation, J. Smith, and another may reverse the order of family and given names. Before comparing records, we need to put them into a common shape. In this POC, name standardization will convert names to uppercase, remove punctuation, split names into words, remove empty tokens, sort the name tokens alphabetically, and join them back together. Token sorting is especially useful for names that appear in different orders. For example, Tran Van Nguyen and Nguyen Tran become much more comparable after sorting the name tokens. It is not a perfect solution, but it is simple, explainable, and useful for this POC. Stage 2. Candidate generation. Imagine one system contains 1 million records and another system also contains 1 million records. Comparing every record with every other record would require 1 trillion comparisons. That is not practical. Candidate generation reduces the number of comparisons. We only compare records that share some basic evidence. For this POC, a pair becomes a candidate when it shares at least one of the following: the same email address, the same date of birth, or a similar sounding name token. To identify similar sounding names, we will use SoundX. SoundX converts a word into a phonetic code. For example, brown and brawn produce the same SoundX code. That allows us to nominate them as a possible pair. But candidate generation does not mean they are a match. It only means these two records are similar enough that we should compare them more carefully. Stage 3, similarity scoring. Once we have a candidate pair, we calculate a similarity score. In this POC, we use Levenshtein distance. Levenshtein distance counts how many single-character edits are needed to turn one string into another. For example, John Smith to John Smith requires 1 insertion. We then normalize the result into a similarity score between 0 and 1. A score of 1 means the names are identical. A lower score means more edits are required. Stage 4, match classification. The similarity score is then combined with stronger evidence. Our rules are: first, if both records contain the same valid email address, they are a match. Second, if the date of birth is the same and the name similarity score is at least 0.7, they are a match. Third, if the name similarity is very high, but there is no other supporting evidence, the pair should be reviewed rather than automatically merged. Otherwise, the records remain separate. These are deterministic rules. That means a person can read them and understand why a decision was made. That explainability is one of the main reasons we are using rules for this POC. Stage 5, clustering and survivorship. After deciding which pairs match, we assign their source records to a common entity. We then build a golden record. The golden record selects or combines the best available values. For example, we may prefer the CRM name for display, but we may retain both known email addresses. We also preserve the IDs from each source system so that the entity remains traceable back to the original records. Now that we understand the architecture, let us build it. We are going to create the Azure environment using a script rather than the portal. This is an example of infrastructure as code, and there are several practical reasons for doing this. The first reason is speed. Creating every resource manually through the Azure portal requires moving through multiple screens, selecting options, waiting for pages to load, and repeating similar information. With a script, we can define the important values once and run the deployment in one go. The second reason is consistency. When resources are created manually, it is very easy to miss a setting. For example, forgetting to enable hierarchical namespace would mean the storage account is not configured as ADLS Gen 2. With a script, the configuration is explicit. The third reason is repeatability. We can use the same script to recreate the POC in another subscription, another resource group, or another region. We simply change the variables. The fourth reason is review and version control. The deployment becomes code. It can be stored in Git. Another engineer can review it. Changes can be tracked. And the environment is no longer dependent on someone remembering exactly which buttons they clicked. The fifth reason is cleanup. Because the resources are grouped and consistently named, we can remove the complete environment easily when the demonstration is finished. This Azure CLI approach is imperative. It tells Azure which commands to execute. For a more mature production environment, we may use Bicep or Terraform to describe the desired end state declaratively. But Azure CLI is very effective for a proof of concept because it is fast, readable, and easy to demonstrate. Okay, so instead of going through the interface and creating each resource one by one, we can open a Bash terminal and run this script. While this runs, let me briefly explain what it is creating. First, it creates a resource group to keep the entire proof of concept together. This makes the environment easier to manage and delete later. Next, it creates the Azure Databricks workspace. This is where we will run the notebooks, use Unity Catalog, build dashboards, and later demonstrate Genie. The script then creates an ADLS Gen 2 storage account with hierarchical namespace enabled. This provides the physical data lake storage for the solution. Inside the storage account, it creates a landing container for our 3 sample datasets: customers, transactions, and contacts. It also creates a Databricks access connector with a managed identity. This allows Databricks to access the storage account securely without storing keys or secrets in the notebooks. The script waits for that identity to become available, then grants it the storage blob data contributor role. Finally, it outputs the Access Connector Resource ID, which we will use in Databricks to create the Unity Catalog storage credential. The script has completed. Let us list the resources in the resource group. We can see the Azure Databricks workspace, the storage account, and the Databricks Access Connector. Our Azure environment is now ready. The next step is to connect Unity Catalog to the storage account. Within Databricks, we will create 3 main storage governance objects: a storage credential, an external location, and a volume. You can think of them as answering 3 questions. The storage credential answers, who are we? The external location answers, which storage path can this identity govern? And the volume answers, which governed path will notebooks and users actually work with? I will create a storage credential which uses Azure Managed Identity. I then provide the resource ID of the access connector created by our script. Unity Catalog can now use that managed identity when connecting to Azure Storage. Next, I create an external location that points to the POC landing container. Let us test the connection. The test succeeds. Now we will create the main Unity Catalog objects. First, a catalog called POC. Then 3 schemas: POC.bronze, POC.silver, and POC gold. This makes the architecture immediately visible in Catalog Explorer. It also gives us a natural security boundary. For example, data engineers may access bronze and silver. Analysts may only access gold. We also create an external volume called POC.bronze.landing. The volume points to our landing path in Azure Storage. The notebook will access the files through /volumes POC.bronze/landing. This is much cleaner than embedding an Azure Storage URL throughout our transformation code. It also means the pipeline code does not need to know whether the volume is backed by managed storage or an external ADLS account. I will now upload the 3 sample datasets. The customer file contains CRM customer records, the transaction file contains customer payments, and the contact file contains people from a case management system. Now we can begin building the data pipeline. Now, let's start building the Medallion architecture with this notebook. We begin by importing the PySpark functions and window specification. We also define the landing path once. The transformations will primarily use the PySpark DataFrame API. This makes the processing logic programmable, testable, and reusable. Step 1. Bronze ingestion. This function reads a CSV file and writes it into a bronze delta table. The most important setting is infer schema equals false. That keeps all source columns as strings. At first, that may seem unusual. Why not let Spark identify dates and numbers automatically? Because automatic type inference can destroy information. If Spark guesses that a column is a date, an impossible value may become null before we have captured the original input. In Bronze, we do not want Spark making business decisions. We simply want a faithful copy of the source. The function also adds source file and ungested at. These fields give us basic lineage. We know which file delivered the record and when it entered the platform. The POC uses overwrite mode so that it can be rerun cleanly. A production Bronze pipeline would normally use incremental ingestion with autoloader or Lakeflow. Let us ingest the first 2 files. Under the Bronze schema, we now have customers raw and transactions raw. The customer table contains 11 rows. The transaction table contains 16 rows. The duplicate records are still present, the malformed values are still present, and the business fields are still strings. That is exactly what we want. Bronze has preserved the evidence. Our customer data contains multiple date formats, so the helper tries the ISO format first, then the Australian day, month, year format. Using try to date means invalid values return null instead of failing the pipeline. Next, we standardize the customer data by trimming spaces, normalizing casing, and converting dates into proper data types. We then remove duplicates using a window function, keeping the most recent record for each customer ID. Finally, we create two quality flags, isValidEmail and hasValidDob. Invalid values remain visible in Silver, but they are clearly marked for downstream processing. Let us save the result as postcc.silver.customers. Let's validate the resulting Silver table. The customer count has reduced from 11 to 10 because the duplicate was removed. Let us inspect the deliberate defects. C004 contains an email address without a valid top-level domain. The email is preserved, but isValidEmail is false. C008 contained the impossible date. Its DOB is null, and hasValidDob is false. C002 used the day-month-year format. The date has correctly become the 12th of July 1990. That confirms that the parser is applying the expected Australian format. The transaction pipeline follows the same Silver layer pattern. We standardize IDs, parse dates, normalize currency and channel values, and convert the amount into a decimal type. Using TriCast means invalid amounts become null instead of failing the pipeline. We then validate each customer ID against the Silver customer table and create the flag, hasKnownCustomer. Unknown customers remain in Silver but are clearly identified. We also create isValidAmount. For this POC, an amount is valid when it is present and greater than 0. The rule is explicit, visible, and easy to review. Let us save the result as .silver.transactions. Let's validate the transactions table. Two records stand out. T1003 is linked to the unknown customer C999. It also contains a negative amount. T1009 contains no valid amount. Both remain visible. This is useful for audit, reconciliation, and troubleshooting. Silver tells us what is wrong. It does not pretend the bad records never arrived. The Silver tables now contain clean and trusted representations of the source data. Next, we will create gold tables designed for business consumption. The first is a customer dimension. The second is a monthly spend fact table. The customer dimension creates a single customer name. It also calculates an age band. The age bands are under 30, 30 to 49, 50 and above, and unknown. The unknown category is important. A customer with an invalid date does not disappear. Instead, the missing information is represented in a safe, business-friendly category. We also remove invalid emails from the business-facing output. The original value is still available in Silver, but gold only exposes an email address when the pipeline considers it valid. Let us save the dimension as postc.gold.dimCustomer. Now we create the monthly spend fact table. Before aggregating, we keep only transactions that have a known customer, have a valid amount, and have a valid date. This is the first point where invalid transactions are removed from the trusted consumption dataset. The filtering rule exists in one visible place. The grain of the table is one customer for 1 month through one channel. At that grain, we calculate the number of transactions and total spend. The result is saved as poc.gold.fct score monthly spend. Even after the invalid data is filtered in gold layer, they are still fully queryable in Silver. We can now see the architecture directly in Unity Catalog. Bronze contains the raw source tables. Silver contains the clean and validated source-aligned tables. Gold contains the customer dimension and monthly spend fact. This is one of the benefits of separating the schemas. The architecture is visible, it is governable, and users can immediately understand which data is raw, trusted, or consumption-ready. Now that the gold tables are ready, we can build an AI BI dashboard. First, we configured the dashboard dataset by joining FCT monthly spend with DIM customer. Databricks also allows us to use AI-assisted dashboard creation. We can describe the visual we want, and the platform can help generate the chart from our trusted gold dataset. The quality of those AI results depends heavily on the quality of the underlying tables. Clean names, clear measures, and well-designed gold tables give the AI much better context. That completes POC 1. Now let's build on the same architecture and solve the entity resolution problem. Our CRM and case management system both contain information about people, but they do not share the same identifier. Some records clearly represent the same person. Others look similar but should remain separate. First, we need to ingest the contacts file into bronze and silver layers. It uses the same bronze ingestion function. That creates poc.bronze.contacts raw. We then apply the silver pattern. Contact IDs are standardized. Names are trimmed. Dates are parsed. Emails are normalized. Suburbs and states are cleaned, and duplicate contact IDs are removed. The result is popoc.silver.contacts. The important point is that onboarding a new source follows a repeatable pattern. We do not need to redesign the entire platform. The new source moves through bronze and silver just like the existing sources. The first stage of entity resolution is standardization. Our CRM and case management systems store person data differently, so before comparing records, we bring both sources into one common schema. For each record, we keep the source system, the original source ID, the raw name, date of birth, email, and state. For CRM records, we only include the email when it passed the silver layer validation. This prevents an invalid email from being used as strong matching evidence. We then standardize the names by converting them to uppercase, removing punctuation, splitting them into words, and sorting the name tokens. This reduces the impact of different name ordering across systems. Finally, we combine the CRM and case management records into one table and save it as pop.silver.personSource. This common person table becomes the input for candidate generation and similarity scoring. Next, we move through 3 stages together: candidate generation, similarity scoring, and match classification. First, we separate the common person table into CRM records and case management records. We then create candidate pairs. A pair becomes a candidate when the records share the same email, the same date of birth, or a similar sounding name token based on Soundex. This reduces the number of comparisons while still capturing likely matches. For each candidate pair, we calculate a name similarity score using normalized Levenshtein distance. The score ranges from 0 to 1, with 1 meaning the names are identical. We then apply the match rules in order. An exact email match is classified as a match. A matching date of birth combined with a name score of at least 0.7 is also classified as a match. A very similar name without supporting evidence is marked for review. Everything else remains a non-match. Finally, we save the scores and decisions to poc.silver.er scored pairs. This table provides an audit trail showing which records were compared, their similarity score, and why each decision was made. Now that we have pair-level match decisions, we need to convert them into resolved entities. First, we keep only confirmed matches. As a defensive step, if one case record matches more than one CRM customer, we keep the match with the highest similarity score. Next, we create an entity cross-reference. Each CRM customer becomes the anchor for an entity ID. When a case record matches a CRM customer, it is assigned to the same entity. If a case record does not match anyone, it receives its own entity ID. We then combine the CRM and case system mappings into one table and save it as poc.gold.entityxref. This table preserves the relationship between every source record and its resolved entity. The next step is to build one golden record for each resolved entity. We join the cross-reference table back to the standardized source records, then group everything by entity ID. The survivorship rules decide which values appear in the final record. For the display name, we prefer the CRM name when it is available. Otherwise, we use the case system name. We keep all distinct email addresses and states, rather than choosing only one. We also preserve the source system records that contributed to the entity and count how many records were combined. The result is saved as poc.gold.entitymaster. This table provides one consolidated and traceable view of each resolved person. The final step is to make the resolved entities easy to use. This search function accepts part of a name or email address and searches the golden entity table. It checks the preferred display name, both source system name variations, and all known email addresses. The result returns the entity ID, key details, record count, and the source records behind each entity. We can then test the search using terms such as Smith and Win and King. This gives users a simple way to find resolved people while still seeing the lineage behind each result. The Python helper works inside this notebook, but we want dashboards, SQL users, and Genie to access the same capability. So we register the logic as a Unity catalog table function. The function is called poshi.gold.searchEntity. It accepts a search term and returns a table of matching entities. This gives us one governed definition. The search logic is not copied into multiple dashboards. It is not re-implemented by every developer. It is created once and reused everywhere. Now, let us use the entity search outside the notebook. First, we create an AI/BI dashboard that calls pot.gold.searchEntity. The dashboard includes a text parameter called searchbox. When the user enters a name, the dashboard passes that value to the function and displays the matching entities. The important point is that the dashboard does not contain the entity resolution logic. It simply consumes the governed search capability created by the pipeline. This keeps the complex logic in one controlled and reusable place. Another way to consume the entity resolution capability is through Databricks Genie. Genie allows users to ask questions in plain English instead of writing SQL. The Genie space is connected to the entity master table and the governed search entity function. We also instruct Genie to use that function when users search by name or email. This ensures Genie reuses the same approved logic rather than creating a different interpretation. For example, we can ask, find people named Smith, or is there anyone called Nguyen? Genie returns the same resolved entities as the dashboard. We now have two user experiences, a structured dashboard with a search box, and a conversational interface using natural language. Both rely on the same governed gold data and produce consistent results. Let us review the full solution. At the Azure infrastructure layer, we created a resource group, an Azure Databricks workspace, an ADLS Gen 2 storage account, a landing container, a Databricks access connector, and an Azure RBAC role assignment. We created these resources through a repeatable script rather than relying on manual configuration. At the governance layer, we created a managed identity storage credential, an external location, a governed Unity catalog volume, a catalog, and separate bronze, silver, and gold schemas. At the medallion layer, bronze preserved the raw customer, transaction, and contact data. Silver cleaned, typed, deduplicated, and validated the source records. Gold created business-facing dimensions, facts, and reusable data products. At the entity resolution layer, we standardized person records into a common format, generated candidate pairs, calculated fuzzy name similarity, applied explainable match rules, created an entity cross-reference, and built golden entity records. Finally, we exposed the data through an AI/BI reporting dashboard, an interactive entity search dashboard, and a Databricks Genie natural language experience. This proof of concept intentionally keeps several areas simple. The tables are rebuilt using overwrite mode. A production pipeline would normally use incremental ingestion with autoloader or Lakeflow. It would use merge operations for updates and potentially slowly changing dimensions for history. The quality rules are implemented as explicit flags. A production solution could add Lakeflow expectations, quarantine tables, and monitoring. Candidate generation uses a direct join condition because the datasets are very small. At enterprise scale, we would materialize blocking keys and use efficient equi-joins. The name comparison uses Levenstein similarity. A production solution may also use Jarrow-Winkler similarity, nickname dictionaries, phone numbers, addresses, government-issued identifiers, or a probabilistic entity resolution framework such as Splink. The thresholds in this demonstration were calibrated to the sample data. Production thresholds should be tested using labeled examples of true matches and non-matches. The clustering model uses the CRM as an anchor. With more systems or with in-source duplication, we may need graph-based connected components. And finally, the review category does not yet have a human review workflow. A production implementation should allow authorized users to review uncertain pairs and preserve their decisions. Even with those limitations, the POC demonstrates the complete architecture and the main design decisions. And that completes the demonstration. We went beyond the medallion diagram and saw what each layer does in practice. Bronze preserves the source data. Silver creates trusted and auditable records. Gold turns that data into reusable business capabilities. We then extended the platform with entity resolution, using explainable rules to handle spelling differences, missing values, name order variations, and uncertain matches. Finally, we exposed the resolved entities through a governed search function, an AI/BI dashboard, and Databricks Genie. The key message is that these concepts are not only theoretical. They can be implemented step by step using clear transformations, visible quality rules, secure access, and reusable governed logic. A strong data platform is not only about processing data quickly. It is also about preserving lineage, making quality visible, and keeping decisions explainable. Thank you very much for watching.